Hello, Professor Marloes. What are we going to talk about today?
Hi, Ivan. I want to talk about satellites and how they view the Earth and what we can learn from them. The satellites orbit around the Earth. That means that they are, if we take the apple as the Earth, and we have a satellite here, they look at different positions on the Earth from a very large distance. So let's start with the geostationary satellites. That's the satellites that look at one position on Earth all the time. So they move as the Earth is turning, they move with the Earth, and they always view the same place on Earth.
That would be, for me, standing on Earth would be stopped, basically.
Exactly, it would always be looking at you.
Yeah.
Then we have the polar satellites. They revolve around the Earth in an orbit. And as the Earth turns, they scan a different bit of the Earth. So in contrast to the geostationary satellites, which were far away, which we had before, they see all of the Earth in the course of one day. But they pass over at essentially the same local time. So let's say we have a satellite that passes over, that sees the Netherlands at 1 o'clock. Mm-hmm. It will always see the Netherlands at 1 o'clock, never at 2 or at 10 a.m. or something like that.
Okay. Why is that useful?
It's useful because if you want to look at changes in trends, or you want to look at a time series, you want to have the same conditions, more or less, so that you have a very stable time series, so that you can look at that. On the other hand, it's also a disadvantage because sometimes you would like to know what changes occur during the day. Mm-hmm. For example, clouds, they have a very distinct daily cycle in some regions. Yeah. So that's sometimes it would be interesting. Then we have the geostationary satellites, which can then see everything during the whole day.
Okay. And there's one more type?
There's one more. There's lots. There's lots of types. Are you thinking of one in particular?
Oh, for me, what I do look at the movement is from the International Space Station.
Ah, yes. The International Space, the speed, let's say, at which a satellite is traveling depends on the height of its orbit. So these geostationary satellites are really far away, 35,000 kilometers. The ones I told you about before, the polar satellites, are about 800 kilometers from the Earth. And then we have the ISS, that's a little bit lower. Again, I think it's 500, something like that, 500, 600 kilometers. And that's in neither orbit. So it views parts of the Earth at different times of the day. Mm-hmm. And the ISS is, of course, very special. It is a satellite. It's orbiting the Earth, but it's inhabited. There are people there. Whereas all other satellites do not have people living on it. And sometimes this is annoying because even in space, things can go wrong with satellites, and you can't just go there and repair it. If it's wrong, you have to fix your computer algorithm to make
to compensate.
To compensate, exactly, to correct for those errors.
Okay, so basically what we do here at the faculty is to look at images that come from the satellites. And what does the satellite see?
That's a good question. I think the better question is what does the scientist see? Because the satellites. Well, first of all, there's a very wide range of satellites. Most of them are looking at radiation, and radiation is not just something that's dangerous. Radiation is everything from light to radio waves and beyond. Mm-hmm. So light waves are relatively short. Mm-hmm. And they are observed by a lot of different satellites. These can be used to look at the Earth. For example, if you have a satellite that looks very closely at the land cover, you can, if you make a picture every time, the satellite makes a picture every time, you can make a time series and look at if there's changes in the land cover. But there's also more information that humans cannot see in these data. For example, what I've been working on a lot is atmospheric composition. So if you have a certain satellite instrument that that measures a very wide range of wavelengths, so very different colors of light. You can sometimes extract...
So when we're talking about wavelengths, we're talking about, let's say, visible light would be from red going to orange and so on until blue and violet?
Yes, I mostly think the other way around, because blue has the shortest wavelength and red has the largest. And after red, if the waves become longer, you get the infrared, which is not, we cannot see it, but we can feel it usually, the warmth. And after that, well, the waves get longer and longer. You go into the microwave range and then into the millimeter wave and radio waves.
Okay. And to the other side?
To the other side, it gets shorter and shorter. So you go to gamma radiation, things like that. I don't think anybody is using the gamma radiation for satellite measurement, at least not for Earth observation, because the atmosphere is impenetrable. So you would just not see very much. Okay. That's also the case for the UV. I think you know, well, most people know about the ozone layer, which is protecting us. This is because this ozone layer absorbs all of the UV radiation, which then doesn't reach the Earth. Vice versa, that means that if you have a satellite instrument that's looking down at the Earth, it will not see through the ozone layer because there's no, because the radiation just disappears, the light disappears there.
I see.
So we're often using visible light. And what I wanted to say is you can look at atmospheric composition, so what is in the atmosphere, how much is in the atmosphere. For example, I'm now working with ammonia. This is most famous as coming from cows, and you can smell it in the air. And this you can also see with satellite instruments. If you use the correct computer programs or an algorithm to derive the ammonia concentration, we can see where the sources are, so where are the farms, or there might be a lot of other different sources, and where is it going? And the nice thing is, if you have a satellite, you can look at a very large region every day anew.
Could you give an example of the use of infrared, so below visible light?
Yeah, beyond visible light. So the infrared has larger wavelength. It's what we also, well, it's also called thermal radiation. And one thing you can do with thermal radiation is you can look at the height of clouds, for example. So clouds, they seem very simple. If you look at them, they're white. And the reason that they're white is because they don't absorb radiation, but they reflect it essentially. So we can see clouds as white, but a satellite instrument that measures in the infrared would also see them in a different way. So what it sees is that the radiation cannot go through a thick cloud, and so what it then measures is the temperature of the top of the cloud. And if you then have a model which tells you what height, which temperature is at what height, then you can look at where the cloud is located, at what point is the cloud top height. And this is interesting because this goes into weather models. It says something about the type of cloud. It tells you if it might rain or if there might be hail or things like that. So it's very interesting to meteorologists.
And this is how we know when it's going to rain in the Netherlands.
Well, we never know when it's going to rain, right? But this is information that goes into weather models, and that's one reason that the weather models have become much, much better. I mean, of course, they're still not right in predicting the rain, at least not all of the time. But weather models have become very much better because there's so much more information. That's one reason. But one reason is that there's a lot of information going in there, and this comes from satellites. It's not only the clouds, but it's also, for example, the water vapor. So water is also in the atmosphere. And if you know how much is there, then you will also know something about how the energy in the atmosphere is distributed and where the water might go to form clouds and all of this meteorology stuff that goes into these weather models.
Okay. And how do we get images from the satellite down to Earth?
That's a very good question. There's a region in the radiation wavelength. I talked about the wavelength before. So we started at the gamma radiation, and we went to the UV, and we had the visible, and then we have the infrared, and there's a lot of more things going on. And there's a region that's very transparent to radiation. So the atmosphere does not do anything with that radiation. Let's go through. That's a radio. That's why we use it for radio communication. That's also the way that satellites communicate their information to Earth. So they have a sender and they disseminate the information down to Earth. But that's not the information that I get, for example. So because that's just a bunch of accounts. The satellite instrument tells us, okay, I saw one photon there and I saw one bit of light there. This goes to a big data center, for example, for a UMATSat, that's where a lot of European data goes. And they first do a lot of calibration and calculations, and they have to put in, they have to calculate exactly where the satellite was when it was measuring, at what altitude it was, and things like that. And that all goes into a very big data set. And this data is then sent out around the world. We can download that data set and then we can work with that. But still, there's a step in between, because this is still just the light that the instrument received. And that's not what we want to know. We generally want to know something like, well, where was the cloud? And then we use an algorithm. So scientists have developed programs that turn the information from the satellite into information we can really work with, like cloud cover, cloud height, or ammonium concentration. Okay.
And after satellite just passed above us and took a picture of us, how long till we get that data?
The satellite information comes down very quickly. The one big step is this calibration that has to be done on Earth, but there are near real-time data. So it's not real-time, but it's near real-time data that can be present within an hour or an hour and a half, which is of course necessary for weather forecasting. You need to have the information as soon as possible so that you can give out your forecasts as soon as possible.
Great. Well, thank you very much for this video, Professor.
Thanks, Ivan. It was fun.
Do you want to be a Geohero as well? Then take the first step and click the subscribe button and then the bell button to always be the first to know when one of our Geoheroes posts a new video.